So last session, we stopped here with Codex, or the product version of it being GitHub Copilot. And please make sure that if you can play around with Copilot, try to do that. It's a good exercise. And try to gain access to Copilot. I'm not sure if it is publicly available or no, but you can get an idea of how a product coming out of large language models is going to look like, and how you can actually help software engineers perhaps remember a command that they forgot. And with that, we can close the chapter of language modeling and move on to multimodal learning. Why would you try to do multimodal? Because we are trying to go after general AI, human level AI, and we as human beings can process data at multiple modes. And by that, I mean, we can listen to somebody, we can look at images, and at the same time understand language, understand commands, and perform different tasks in the physical world. And we want to expect the same thing from our AI system. And the other motivation is when we were considering GPT, we start talking to it, perhaps GPT-3, and it's gonna generate some reasonable text. And at some point, it's not gonna be reasonable at all. It's just gonna keep outputting words or sentences that don't really make sense. And people thought that maybe GPT is making mistakes because if it is talking about something, it has never seen it before. Maybe if it is describing a car, it has learned it only from text. It has never seen the image of a car. And that's why multimodal matters. And these days, there is a lot of effort towards multimodal learning. I start with this paper, which is about visual recognition and description. We have spent a lot of time last semester, or actually last year, going through this paper. The video is online, so I'm not going to spend too much time on it, just summarizing the key points, and then you can ask any questions that you might have. What are the type of tasks when you're doing multimodal learning at the intersection of images and text? One of them could be activity recognition, which is that you have an input video, which is a sequence of images, and then you want to say, what is that video about? Try to recognize the activity. And why is it important? Because later on, if you are looking for something, maybe you are looking for people playing soccer, you want to find videos like that. When you search for them on Google, then Google is going to go the reverse route. It knows the video. The videos are going to be on YouTube. It knows the corresponding label for it. It's going to know that these people are playing soccer. And once you search for playing soccer, but your actual intention is not the word itself, but you're actually looking for a video of that, the video is going to show up. That's why video activity recognition is important. And actually in part 1 of the course, we have spent a lot of time on that. And for that, a good data set to explore is UCF 101. It has 101 categories or different types of activities. And this is where you have a sequence of images, you're outputting a single output. The other one is really important. We are going to spend some time on it, is you have an image and you want to output a text. And that one is image captioning. And this is helpful when you want to have a product for visually impaired people on the web. Or sometimes you want to understand what a CNN is actually thinking about. Why is it giving you this caption? Where in the image is it looking at? And it's one way of opening the black box of a CNN and try to understand its thought process. And basically the AI system is speaking to us in plain English language or in any other language. The other one is you have a video as input and then you are outputting a caption for it. And it's video caption generation. You can go the reverse route, and that one has to do with generative models, especially GANs and those sorts of topics that we're going to cover later on, where you go the reverse route. You have a caption, and then you want to generate the corresponding image. And in that case, your neural network is actually imagining an imaginary scenario. And I try to give you realistic looking images. And we're going to cover all of them. The other one is you have a text, you have an image, you want to embed them in the same embedding space or in the same vector space. And that one we are also going to see later on. That one is useful when you want to do data augmentation. But in terms of architecture, it doesn't really matter. If you have images, perhaps you can process them with CNNs, or these days people are using vision transformers or MLP mixer type of architectures, multi-layer perceptron mixer. That one we cover in part 1 of the course. If you have a sequence of vectors, you can process them using LSTMs, RNNs, GRUs, or transformers. And in terms of outputting the predictions, we usually have a softmax, and it's outputting a text for us. Or you're going to have a softmax at the end, outputting a single class. In terms of evaluation metrics, it depends. If you are doing activity recognition, that's a classification task, and perhaps accuracy is a good metric if your data is balanced. If it's unbalanced, something like F1 score, the average of recall and precision. If your task is a little bit creative and it's not unique, for any image, there could be multiple good captions, the same way that you had for any English sentence, there could be multiple good French translations, and they're all equally as good as each other. In those cases where you have a one-to-many mapping, blue score could be a metric that you can use to compare different methods together. These are two good data sets to work with. And be careful with Microsoft Cocoa if you decide to explore it. It's some portion of that is actually for object detection, and the other portion is for captioning. So if you decided to explore this, don't explore the object detection. That one we are going to cover in part 1 of the course. You can explore the captioning part of that data. If your task is retrieval, you're searching for something, you can look at median rank, or you can look at recall. And there is also a limited availability of data issue, because generating captions for images, you need a human to do so. And then it's actually much more costly compared to, saying that in this image there is a cat, there is a dog, doing classification. Now somebody has to actually write down a sentence. And therefore you're going to have less data. And the problem with having less data, we are going to attack it in the next paper, in the next slide, or the one after it. But for now, are there any questions about LRCN, long-term recurrent convolutional networks? Was everything clear?
What is the output of the CNN feature into the LSTM? Is it going to be an embedding, or is it going to be the 2D feature maps?
No, it's going to be vectors. You take a tensor. We know that images are tensors. They're going to have a height, a width, and 3 channels, red, green, blue. And the entire purpose of your CNN is to featureize it. And whenever I say feature, it means that you need to get a vector out of it. So each one of those images, you're going to vectorize them, and then you're going to have a sequence of vectors to work with.
Okay, thank you.
Like before we talked about blue scores in the context of like translation, but is the blue score for like convolutional networks sort of the same?
Oh, so we are not doing blue score for images. We are doing actually blue score for these English sentences, for the captions that are coming out.
Oh, I see.
So the CNNs here are actually to give you vectorized representations of your images.
I see.
But the output of the model, when it comes to image description, is going to be a sentence. And whenever you have a sentence, you can actually look at the blue score between this sentence and the ground truth. Because this sentence that comes out of this framework, the caption, could actually end up being really bad, because it's actually a model. It's not the ground truth. And then you want to measure its goodness. Well, these are good questions. Any other ones?
And then those predictions in the chart in the top left, those can be either like video description labels or image labels or any of the 3 types.
You said top left?
Yeah, so like the predictions, the vector of predictions.
Yes. So
okay.
What are we plotting here in terms of your architecture? You are just plotting the things that are parameterized. You are not plotting outputs. CNN is parameterized, LSTMs are parameterized, so they're going to have their own parameters. And these other ones are fully connected. And therefore, it's enough to show the vectors, the actual weight matrices. I think if I rotate this figure, you're going to understand it more, because then it's going to be a sequence going in, a sequence coming out. And we had the same architecture when we were doing perhaps translation. Now you're translating from a video, a sequence of images, to a sequence of text, or a sequence of one-hot vectors, or a sequence of probability distributions. And usually at the last layer, this is exactly what we do. We get the output of LSTM multiplied by a matrix to give us the number of words that could happen at the end. And these are our, the size of that is going to be your vocabulary size. So does that answer your question?
Yes, thank you.
Yeah, sure. Any other ones? Okay, perfect.